Neurons communicate over long distances by generating and sending electrical signals called action potentials. Most action potentials originate in the axon's initial segment, a region also called the trigger zone. During an action potential, voltage-gated sodium and potassium channels open and close, thus altering the membrane's permeability to sodium and potassium ions. As these ions diffuse through the channels, the membrane potential changes. It depolarizes from the resting state of minus 70 millivolts to a peak value of plus 30 millivolts, and then quickly repolarizes back to minus 70 millivolts after a brief period of hyperpolarization. In this topic, we explore, step by step, the events that occur as an action potential is generated in the axon's initial segment. The action potential begins when local signals originating from the dendrites and cell body reach the axon's initial segment. These local signals, also called graded potentials, are very different from action potentials in that they are short-lived and their magnitude decreases with distance. However, when their magnitude is great enough, they produce currents that spread all the way to the initial segment. When this occurs, it causes the membrane potential to depolarize to a critical voltage called threshold. Threshold is the membrane potential that must be reached in order to generate an action potential. Its value is about minus 55 millivolts. The membrane depolarizes further to a peak value of plus 30 millivolts. The membrane then repolarizes and returns to minus 70 millivolts following a brief period when the membrane potential becomes more negative than the resting state. This period is known as hyperpolarization. If the currents arriving at the initial segment are insufficient, and the change to the membrane potential is below negative 55 millivolts or subthreshold, then no action potential fires. In fact, action potential generation is an all or none event. Either it happens or it doesn't. When the initial segment depolarizes to a suprathreshold value, even one that is way past threshold, an action potential of the same amplitude is produced. Action potentials are always the same. The amplitude never varies. The sodium and potassium ion channels involved in the generation of an action potential open and close in response to changes to the membrane potential, or voltage. Thus, these channels are voltage-gated. The voltage-gated sodium channel has two distinct gates. One is an activation gate. The other is an inactivation gate. The two gates open and close, alternating between three different states. The first state is the closed state that we observe at the resting membrane potential. The inactivation gate is open, but the activation gate is closed. No sodium ions can pass through the channel. The second is an open state. With sufficient depolarization, the activation gate opens, permitting sodium ions to pass through the channel. The third is an inactivated state, observed during repolarization. The activation gate remains open, but the inactivation gate closes. This blocks sodium ion diffusion once again. In order for the channel to reopen, it must first return to its closed state. The voltage-gated potassium ion channel is simpler because it has no inactivation gate. It has a single activation gate that alternates between being open or closed. At the resting membrane potential, the activation gate is closed. With sufficient depolarization of the membrane, the activation gate opens, allowing potassium ions to pass through the channel. Now let's compare the two channels side by side. The sodium ion channel has two gates. One is an activation gate, and the other is an inactivation gate. In contrast, the potassium ion channel has only a single activation gate. Both channels are closed when their activation gates block the diffusion of their respective ions. Note that in this closed state, the sodium ion channel's inactivation gate remains open. Both channels permit the passage of their respective ions when their activation gates swing open. In this open state, the sodium ion channel's inactivation gate remains open. As stated before, the sodium ion channel has an additional state that we don't observe in the potassium ion channel. This is an inactivated state in which the activation gate remains open, but the inactivation gate closes. Let's examine the phases of an action potential. We start at the neuron's resting state. A threshold stimulus opens both voltage-gated sodium and potassium ion channels in the neuron's membrane. However, these two types of channels open at quite different rates. Sodium ion channels are quick to open in response to the stimulus, while potassium ion channels are slower to open in response to the same stimulus. Let's take a closer look at this again. As the activation gates of some voltage-gated sodium ion channels open, sodium ions diffuse into the cell. Sodium ion entry depolarizes the membrane further, which opens more sodium ion channels, leading to even greater sodium ion influx. This establishes a positive feedback loop that switches on as the membrane potential passes threshold. Depolarization of the membrane opens sodium ion channels. Sodium ions enter the initial segment and depolarize it further. As more sodium ion channels open, we observe a rapid depolarization to a peak value of plus 30 millivolts. This constitutes the depolarization or rising phase of the action potential. An abrupt decline in the membrane's permeability to sodium and an increase in its permeability to potassium mark the end of depolarization and the beginning of the repolarization phase. Voltage-gated sodium ion channels, which began to inactivate late in the depolarization phase, continue to close their inactivation gates. Voltage-gated potassium ion channels, which began opening during the depolarization phase, continue to open. At the peak of depolarization, more potassium ions are leaving the neuron than sodium ions are entering, and the membrane potential begins its return to a negative value. We now enter the repolarization or falling phase of the action potential. Notice that potassium ion diffusion out of the neuron continues beyond the point of restoring the membrane potential to its resting state. The membrane potential actually hyperpolarizes to about minus 80 millivolts, thus producing the hyperpolarization phase of the action potential. Ultimately, potassium ion channels close and the membrane returns to its resting state. By this point, all voltage-gated sodium ion channels have reset to their closed state. This means their inactivation gates are open and their activation gates are closed. A common misconception about this process is that a huge number of sodium and potassium ions must cross the membrane to produce an action potential. In reality, relatively few ions move, and the concentration gradients between the inside and outside of the neuron remain essentially unchanged. However, the sodium and potassium ion gradients can be disrupted after the repeated firing of thousands of action potentials. Over the long term, neurons rely on sodium-potassium pumps to maintain these gradients. Let's review what you have learned about the generation of an action potential. Voltage-gated sodium and potassium ion channels are closed in a neuron at rest. A stimulus that reaches threshold slightly depolarizes the membrane of the initial segment, or trigger zone, where the action potential originates. At this point, some voltage-gated sodium channels open, allowing sodium ions to diffuse inward. The membrane depolarizes more, and a positive feedback loop is initiated that opens all voltage-gated sodium ion channels in the initial segment. During depolarization, the membrane potential surges to plus 30 millivolts. And it is during this phase that voltage-gated potassium channels begin to open. At the end of the depolarization phase, voltage-gated sodium ion channels inactivate, as more voltage-gated potassium channels open. Potassium ions then diffuse out of the initial segment, and the membrane repolarizes back to a negative value. Voltage-gated potassium ion channels remain open after the membrane potential reaches its resting state, and the initial segment hyperpolarizes. As the membrane potential returns to the resting state of -70 millivolts, all voltage-gated sodium and potassium ion channels revert to their closed states. Over time, the intracellular and extracellular concentrations of sodium and potassium ions are maintained by sodium-potassium pumps.